are you guys? Nice to meet you again. Okay, no. Good. All right, Siti. So let's look your attendance for today. Calendar done listed. Okay, we have 50 students. Okay. Can you see my screen, right?
Boleh sir.
Yeah. Okay. For today, we will continue our topics, right? For the test one, right? The date. We as a lecturer, we don't know yet the date for the test one. Okay. Okay. So last Sunday we have learned about time response, right? So we are given a type of input, like step input and so on. So and then we will get the output, right? The output will be have some transient state, right? Which is the state where the output will be that means it's not stable yet, and then after that it will be stable or it will be at steady state error. Okay, and then we use the Laplace transform to solve the differential equation, and then we have done some equation from the system, and then from this one we come out with we do some basic thing about the Laplace transfer function, and then we are given Laplace table. So how to solve it, right? So based on the table, and I did the example. You can use the Laplace, right, to solve the differential equation. Okay, this is the differential equation, and then you can use Laplace, right? Okay, and then we also done the example 2.5. You use the Laplace, and then at the end, when you apply the input, right? For example, the step input 1 over s for Laplace, and then you will have some what we call it equation, and then how to solve this one, right? To make it in partial fraction. So this is what we will learn for today. Okay, so partial fraction, you can use the remainder theorem. Okay, so um, the advantage of this remainder theorem is uh, the this one we call it the partial fraction. We can it can be solved using the remainder theorem. So how to solve it, right? Look at this one. The output, right? For example, y. So is equal to numerator over the numerator. Okay. So you need to make it as what we call it the roots, right? Then you need to multiply with the roots. So we will go some example on that. Okay. This one I think you have learned in Form 5, right? In AddMath, right? So let's look a little bit about this one. Okay. If you have any question, you can ask, right? Okay. Yeah. Okay. Right. So today I'm using the new cam and also the new software. All right. So example 2.6. Now you got it the equation. Okay. D squared. So let me do like this one. Dy. Okay. Plus 5 d plus 6y and plus 12 et. Okay. So now when you Laplace, Okay. Now when you Laplace, that means you Laplace all these things. So first of all, let Laplace d squared y. Then right, you will got it is s squared ys, right? This the small letter. Then when you Laplace it, it will become the capital letter. And then this one is s y naught. Okay. Right. So then y and 0. Okay. Then right. And then when we Laplace, when you Laplace 5t, so it become 5 multiply with s ys minus with y. Why we call it y naught? Okay. Right. When you look at the table, right? Where is the table? Okay. This is the second derivative, right? When you Laplace it, so you will got it this one, right? S, this mean y is 0 and y, what we call it, this one, right? So 0 here, and then when you Laplace this one, you got it y and 0 here, okay? And then this one, right? And then the next one, and you Laplace sec y, it will become sec ys, right? And then when you Laplace 12 et, now it become 12 et also. Okay, done. So next you apply where is it? Okay, y0 equal to 2 here. So this one equal to 2. And this one y dash, right, equal to 1, right? Y0 equal to 2. Okay, then you need to combine it back. So you got it as y ys minus 2 s minus 1 plus 5s ys minus 2 plus 6 ys. Okay, and then sorry. So this one when you Laplace it, right? Et that means it become 1 over s minus 1, right? So this one you can look at the table, okay, s minus 1. Alright.
Doktor.
Yep.
Sekejap. Yang minus 2 tu sepatutnya jadi minus 10.
Minus
Multiply.
2, minus 2, minus 10. Okay, which is it? Where is it? Okay, good. Thank you. So this one 5 times 2. Thank you very much. Minus 10. Good. Alright. And then when you solve this equation, right? So you will got it, the final one, ys equal to 2s squared plus 9s plus 1 divided with s minus 1, s squared plus 5s plus 6. Okay, so this is the final one, right? So this one we call it partial fraction. So how to solve it, right? Uh, how to solve it? So you got it to s squared plus 9s plus 1 divided by s minus 1. So this one you can factorize it, right? So s plus 2, s plus 3. Okay, this is the final one, fs, done. Then how to make it a partial fraction? So this one 2 9s plus 1, you divide it with s minus 1, s plus 2, s plus 3. So this one, there are three roots, right? Minus 1, plus 2, and plus 3 here. So you can make it is a1 divided with s minus 1 plus a2 divided with s plus 2 plus a3 divided with s plus 3. Okay, done. So now we want to find what is this, the a1 value and a2 value and a3 value. Okay, right? Right. Boleh? So far okay? Ada apa-apa soalan? No? Simple, right? Do you have any question? Yep.
Buat masa ni okey je, buat masa ni okey.
Oh, sini okay eh? Okay, good. Okay, wait, I need to delete it first. Okay. Now, you got it is, you want to find the A1, so is equal to 2s9 squared plus 1 divided with s minus 1, s plus 2, s plus 3. So, A1, that means is A1 over S minus 1. So that means you need to time with S minus 1. And then you apply S equal to 1, right? That means S minus 1 equal to 0. So S equal to 1. Okay. So before you apply it, right, you need to cancel out the denominator. And then you can apply. So 1 we apply this S squared, and 1 we apply with 9s, right? 9 times 1 plus 1, and 1 we apply this one, 1 plus 2, 1 we apply this one, 1 plus 3. Okay, and then you got it, the output is equal to 1. Right? Same thing with A2, 2s squared plus 9s plus 1 over with s minus 1, s plus 2, s plus 3, and then A2 actually is over s plus 2, and then you need to multiply with s plus 2, and then you apply the s is minus 2. Okay, right? So before you apply, then you need to cancel out this denominator first, and then you apply. Minus 2 apply to s squared, right? Minus 2 apply to s, 9 times minus 2. Then you will got it, the answer is equal to 3, okay, for A2. And the rest for A3, when you do the same thing, you will got it is minus 2. Right. And the final one, ys is equal to 1 over s minus 1, right, here, okay, because the a1 over s minus 1, and then minus 2 over s plus 2, and also, sorry, this one you got it 3, so 3, all right, and then plus 3 minus 2 s plus 3. Okay, so this is the final one. Because we want to get it the from that equation, so we can divide it into a few fractions. Okay, and then after that you can use the inverse Laplace, right, to get it is yt. Alright, when you want to do the inverse Laplace, so you can inverse all these things. Then minus, okay, so 1 over s minus 1, right? So when you look at the table, s minus 1, this one s minus a. Then you got it is a exponent t, right? Exponent t, and plus with 3 e minus 2t, and then minus 2 e minus 3t. Okay, so this is the final one. Okay, alright, let's look. Okay, so far do you have any question? Ada apa persoalan? Okay, is it clear? Alright. Okay, good. So this is how you apply the remainder theorem. Okay, remainder theorem. Alright. Okay, and then the next example is the same thing, right? It given you this one, so you can use it to remainder theorem. Okay, so you can factorize it, right? Factorize it first. So this one will become a1 over s, a2 over s plus 1, a3 plus s over plus 2, right? So when you solve it, and then here we got it this kind of equation, and then you use the inverse Laplace, and then you can get this equation. Right? The question is how to draw it, right? So you can use MATLAB in order to draw this type of graph. Okay. Okay. And the rest you can apply based on this table lah. Okay. There is one example that you can apply it, right? Because if this one you can factorize it, right? So you can divide it into a few parameter a1 or a2, a3, and so on. If you have squared, so that's mean you need to do like this one, right? X minus a, and then x minus a squared, and so on. And you have what we call this one, power of 2. Is it a quadratic? Quadratic or what? Is it? Apa kita panggil ni? Power of 2 ni. So for example, you have bx power of 2 and so on, and then at this one, right? So you can divide it into this one is nothing. This one, right? Yeah, x power of 2 plus bx plus c, and then you need to divide like this one. Okay, all right. Where the x squared plus bx plus c cannot be factorized further. Okay, this is the remainder theorem. All right. Right. So, do you have any question? No? So far, okay? Boleh faham Alright. So, okay. Let's go for first order system. Okay, the next chapter. Okay. Alright. Okay. So now we have come out with some block diagram from the system. Okay. And then from that system, we also come out with the equation, right, in terms of time response. And then after that, we try to solve the equation by using the Laplace. Okay. And then our objective is we want to plot the equation so that we can see the performance, right, of our system, right? So in order to plot and so on, so we need to do first, we need to know the system itself. That means we need to what we call it classify the system first. Okay, so let's look this system. You got it, the output and then the input, and then K is the controller, and then G is the process, and also sometimes you got the H here, right? Like this one is H equal to 1 as the feedback of the system, right? So there are one words that you will be familiar with it. We call it open loop transfer function. So open loop transfer function is mean that K, right? The controller you time with the process kg, right? So it can be right like this one, K something. So this is the roots for the numerator, and also the bottom one is for denominator. Or we can simplify it like this one, okay? Kg equal to K times S power of M, right? Divided with S L and so on. So what is mean this M, right? This M is used to find the rank, okay? So the most important thing is N, right? The order of the system, okay? For this chapter, we will learn about first order, second order, right? Third order, and fourth order, and fifth order, right? So um, whatever the order of the system, we can solve it, then we can find the performance of the system, okay? So let's look this one, the determine the order, rank, and class, right? So the most important thing is to determine the order of the system. So the order of the system is when you look at the denominator, right? Denominator, okay, yang bawah ni. So that means you need to look at the highest value, alright? So this one will be determine the order of the system, okay? For example, this one S plus 2, and then you can, for example, like this one, the order is the highest one, S power of 4, that means the order equal to 4, right? N equal to 4. That means this is the fourth order system, okay? And then how to find the rank, so you need to do, yeah, you need to take out the S, right? And then 3, that's mean what we call it, the formula is N minus L, and minus L, that mean N minus M, right? N minus M equal to L. So that's mean M, and then you minus with M, and where is it? M, yeah, M is 1. Okay, so 4 minus 1, you got it 3 for the rank. Okay, and the next example is the same thing. You first one, you want to find the order of the system. So S power of 3, you time with S, time with S. So we got it. Oh, this is the fifth order system, right? Okay, and then you can find rank and class. And the rest, when you multiply with S power of S squared, you got it S power cube here, S power of 3, and then that means the order system is what we call it third order system. Okay, so we will look into that first. Okay, let's look the first order system. Okay, normally your test one until this topic, first order system. Okay. Alright, so in general, the first order system, it can be represented as this block diagram and this equation. Okay, the first order system, first order, right? It's like the Star Wars movie, right? You have the first order. Okay, now you have the general equation for the first order system, right? So when you have the first order system, so this will be the general equation for them. Okay, so that means the input xit, this is the in term of time domain. Then this one the k1 plus ds. So k here is not the um, spring stiffness, right? K is mean the controller. Okay, alright. So got it here. Okay, right. You also can write like this one to make it clear for you. This is the K, and then this one is the 1 over 1 plus ds. So this one is x because they Laplace, so if we capital, it's not, and this one is xi. Okay, and when you got a Laplace, so you invert this back, and then you can get it in terms of time domain. T over T, right? So this one is Si of S naught T, and this one is Si T. Okay, so this is the general equation, right, for the first order system, right? And then the graph will be, for the first order, it will be like this one. Okay, for example, when you put it, the step input function, okay? So the input, step input, and then the output will be the same with the step input, okay? Alright, so this is the general equation, okay? Hai, baru nak join ke ni? Alright, K is the controller. K, we call it the controller, or sometimes we call it gain, okay? The controller, okay, the word is controller. Right, and this one we call it is a process, right? So T we call it is the time constant. Okay, what is the time constant? Okay, we will look into that. Okay, so let's look example the first order system. Okay, this is the example of the first order system where you have K, and also you have spring, right? For at the that have the spring stiffness K, and then you have the damper. That's it. Only two components, spring and also damper. All right. And then when you solve it, right, so we get it for force from the spring equal to force from damper here. And then when you solve it, so you will got it this kind of equation, right? And then when you apply the step input function, okay, let me do this one. Okay, now you got it is S naught S equal to K K plus CS and SIS. Okay, and then this one K, you can plus C over K here, then SIS, it's not. Okay, done. And then this CK, that's mean you replace it with the T, right? T is time constant, is C over K, right? So C is the value of the damper, the stiffness value, right? K is value for the spring, okay? So now you got it, the equation is X naught S equal to 1 over 1 plus TS XIS here, okay? And then, for example, is SI is the step input 1 plus TS time with 1 over S here. Okay. Then you will got it, the equation is S1 plus TS here. Then you can do the partial fraction. And then you will got it is 1 over S and minus T 1 plus TS here. Okay. And then this one will equal to 1 minus 1 over T plus S. Okay. We can make it is S plus 1 over T here. Okay. This is, and then when you inverse Laplace, so we got it, that is T. This one is 1 minus E minus T over time constant. Okay, so that's why before this you can see that the general equation will be K time with 1 minus E minus T over T, right? Time constant here. Okay, So for the general equation for the first order, it will be like this one. This is the in term of time domains, and in term of the Laplace, 1 over 1 plus time constant s ds. Okay. So when you try to plot the graph for this equation, so what you can do is you can apply for t equal to t. So you will got it as not t minus what is it? Minus 1. Okay, right? Okay. Minus 1 or minus, yeah, t over t. Yep. Then you will got it as 0.63 something. Okay. And then when t equal to 2t, and then you will got it into t here, 1 minus e minus e2 to 3, so you got it minus 2. So you got it something 0.86. Okay. So when you try to plot the graph, you will got it this kind of graph. Okay. Right. What it means, okay, let me show you something. So far so good. Do you have any question? Ada apa soalan?
Not yet.
Not yet, Okay. So when you try, if you want to use the MATLAB, right? I believe you have learned this one before during your first year, right? Still remember? Masih ingat lagi tak macam mana guna MATLAB? Kita dah lupa dah.
Sikit-sikit saya ingat.
Sikit-sikit Okay. How
Yeah,
about
more-
the rest?
Or
Also,
yeah, more or less lah.
Ingat lupa.
Ingat-ingat lupa. Okay. So, first of all, open the MATLAB, still remember, right? Okay. And then, if you want to write the equation, okay, for example, you want to write this equation, right? 1 minus e t over t time constant. So you can use this unknown, right? Okay, alias t is the unknown. So 1 minus e, okay, yep, this one, okay. This is the separated. Okay, this one, for example, 1 minus exponent minus t over t. Okay, so let's do t, or maybe we can plot it, right? So how to comment this one? Yep. So you can run it. So let's look. You need to make it t equal to 1. Okay, yep. This kind of the graph that we got it here. Okay, when you plot it, so alright, so this is definitely for the x and y axis. Okay, so when you plot the first order system, okay, you can get it this one. Okay, so there are two ways that you can do that. So whether first of all you can using the unknown t, or you can plot it by using the Laplace. Okay, you also can use the Laplace transfer function in order to plot it. Okay, so for example, let's show it to you. You can make it as the section here. So figure 1, this one is 1 over, yep, what is the equation? 1 over 1 plus ds. So 1 plus t times s here. And then we can put it if t, for example, equal to 1. Then we can do this one. Is it we can get the same equation? I'm also forgot about it. Okay, yep. Alright. So this is like the first order term. Okay. Okay. Good. Okay. So you can see that it will have a same value here at the 0.63 here. Okay, so it equal to 1. Okay, here. Okay, this when you want to use the MATLAB. Okay, all right. So I already draw some of the graph here. Okay, so what we can see in this one, right? When you adjust the time constant, here, okay, you will see that the output, right? We try to go to the what we call it, the desired that we want to measure. Okay, I will show it here. Okay. Alright. So, this is our graph for the first order. Okay. That's not T, and this one T. Okay. Then it will stop it at 1. Okay. Why 1? Because our input, right? Is step input that we started the value at 1. Okay, so we're going to achieve this one. Alright, we're going to achieve this one. Okay, so this one we can say that is steady state error here. Okay, ESS. Alright, so when you put it is t equal to 1, so you will see that this kind of graph. Okay, right. When you put it t equal to 2, okay, t equal to 2, that means the graph will be like, yep, okay, like this one. Okay, this one is t equal to 2, right? That when t equal to 0.5, then you will see that, yep, okay, this is the graph. So t equal to 0.5. So what can we conclude from this one is the larger of time constant is t, the slower output response. Alright, because we're going to achieve the output response, right? At the final one, we're going to achieve, okay, this is the error so that we can get it 1. Right? But how much time it will take, right, to achieve to get 1? Okay, clear tak? How much time? Berapa banyak perlukan masa? So maybe this one, when you put it t equal to 2, maybe it will take about 5 seconds, for example. Right? For t equal to 1, maybe it will take about 3 seconds. For t equal to 0.5, maybe it will take about 1 second. Okay? Clear? Boleh tak? When you change the time constant. So how to change the time constant? Remember, time constant t equal to c over k. That means you can change the value of spring and also the damper, right? K you can change and C you also can change, right? In order to play around with the time constant. Okay? Clear tak? Boleh?
Clear.
Ada apa-apa soalan? Tak? Okay. So it's like you want to develop what we call it the suspension, right? So the suspension have the spring and also have the damper. So you can choose the stiffness of that spring and also the damper itself, right? So you can choose the value K and C in order to find the best T, right? The best time constant. Okay? Alright. So this is how you play around with the time constant. And then there are second variable, we call it is k. Okay, so when you adjust the value of k, right, so remember the equation. So you got it is k, and then you got it is right, 1 over 1 plus ts. So this one in term of Laplace, si s, and this one is x naught s. Okay, so okay, this one. Okay, so this one, the one you want to achieve 1. So when the k equal to 1, so this one is k equal to 1, right? That means your controller is equal to 1, right? You don't do anything, okay? So you will got it the same graph with this one, okay? Right? And then now you don't change any value of t, right? You fix the value of c and k, right? And then you play around with the controller, right? This is what we learn about controller. We want change around this one. So let's say you put a k equal to 2, you will see that the output will be like this one. Okay, so this one is k equal to 2, right? So you can see that, yeah, the time that he going to achieve at 1, right, is faster than this one, k equal to 1, right? However, the steady state error, right, for the k equal to 2 is larger. Okay, right. Okay, for example, let's say the air conditioning. So we said it is what we call it, for example, 20 degree. We set it 20 degree. Okay, and when you adjust the fan speed, right? So the fan speed will be your k, right? So now you put it at the maximum fan speed, for example, at 3, right? You put it at 3. So what happened is, yeah, you can achieve at the 20 degree, right? A very faster one, maybe at 1 minute you can achieve, right? Right. However, it will be overshoot. So maybe at this one, at this point, so now it can become 18 degree, okay, because the air conditioning, right? Okay, right. So when you put it the maximum fan, so it will be overshoot 18 degree. Okay, so 2 degree overshoot, right? So we don't want that, right? So this why we call it the test error. So when you adjust the k, yes, you can make it the response become faster, all right? However, you will have some problem there, which is we call it overshoot. Okay, if you uh, put it k equal to 0.5, yep, of course, right? So k equal to 0.5, of course, you got it also steady state error, but the response will be slow. Okay, boleh nampak tak? Can you differentiate between this one when you adjust k and t time constant is fixed? This one, the controller k is fixed, but the time constant will be variable. You adjust the time constant. Boleh? Clear tak? Ada apa-apa soalan nak tanya?
Yang itu faham saya.
Boleh eh? Okay. Any question that you're going to ask? So I forget to look at this chat. Nope. Nope. Okay. Alright. You also can use the MATLAB and how to draw it, right? You can also use MATLAB. Okay. For example, you can put it k time with 1 plus ts here. So k equal to 1, for example. Okay, and then you can repeat it back. Can use the hold on. Okay, this one, right? Try. Long time I not use the MATLAB, right? Okay, so this one need to make it auto exist. Okay. I forgot how to do that. How to make it auto? Okay, equal to 2. And hold on. Done. Yeah. Okay. The red color one, the blue color is k equal to 1. The red color one is k equal to 2. Here. You can see that this is the steady state error here. Right? 2. Yep. Is the steady error equal to 1. Right? 2 minus 1 here. Okay. But the time, right, is it going to achieve at 1. Yep. Compare with this one. With this one. Okay. Right. So this one, it will take about 0.6 seconds, right, to achieve your output that you want. And however, this one will take about 3.9 seconds. Okay. Right. Okay. So this is the first order system. Okay. So let's do example 3.2. 3.2 here. Okay. The transfer function which relate the input voltage and the output torque tau of DC motor is represented by first order transfer function. A time response with 6 volt input voltage resulting in steady state output torque of 20 Newton per meter, and it took about 0.4 seconds to reach 12.6 Newton per meter. Find the transfer function of the motor. Okay, so first of all, we need to gather the information. Okay, what happened here? Okay, so we need to gather the information from the equation, from the question here. Okay, example 3.2. Okay, so now we know that the first order system, it will be K and so 1 over 1 plus ds. This is the first order. Okay, first order. Okay, so now let's say our input is V, right, voltage, and our output is torque, ts. Now when you apply, it says that apply 6 volt here, right? And then the output, we got it here is, it says that 6 volt, it will give you the steady state error 20 millivolt, 20 Newton per meter. So this one is 20, alright? Okay, first order, yep, the graph will be like this one. And it gives you at the 0.4 second. Now you will got it is 12.6 Newton per meter. Okay, so let's check whether this one, okay, is it this one, right, is it the time constant or not? Because we want to find two variable, right? For the first order, we want to find time constant and also the controller, the K here. Okay, right? Because the final one, it will be tau s over ps is equal to K divided with 1 plus ts. Because we want to find the transfer function, right? So it will be like this one. Okay, right. Okay, before that, the time constant here is, that means 63% over the final output. Okay, like I mentioned it before. So we got it 0.63 to 1. That means for final output is 1. 60% of 1, you got it this value 0.63 to 1. Okay. So let's check whether this one is it a time constant or not. So we can do 63 over 100, you time with 20. Right? Now, you got it is 12.6. Okay. Yes, you can get it 12.6 here. Right? You get it 12.6. So that means your time constant is equal to 0.4 second. Okay, now you can get it the first parameter time constant here. Boleh faham tak ini? Is it clear this one? Time constant here is refer to the output that is 63% of the output. Okay, in this solution, I do like this 12.6. So minus with 0 and 20 minus with 0. Right? If your initial value is not start from 0 lah. Okay. If start from 0, so you can take it 12.6 over 20. Alright. Or you can do 63%, you time with 20. So you will got it is 12.6. Okay. Ada apa-apa soalan tak pasal ni? Takat ni clear? Alright. Do you have any questions so far? No?
No, sir. No, sir.
No, sir.
Okay.
No.
Alright. Good. Okay. Now, we got it here. Ts over Vs here. So this one, K1 plus 0.4 S. So now, we already got a time constant here. Okay. Alright. So when we convert it to Laplace, so let's say this t, for example, Vt. So we got it is 1 minus it become K1 minus T minus T over 0.4. Okay. Alright. So how can I get this equation? So remember the general equation K 1 minus E T over T. Okay. Right. Okay. So it become tau term of time domain and what is time domain here. Okay. So K times 1 minus E over T. Here. So let's say T, right, going to infinity and Vt going to infinity. So now you got it is what? 1 minus E minus infinity divided with 0.4. So T going to infinity, that means the tau, right, at the output going to infinity, because this one, right, when going to infinity, you will got it is 20. Okay, 20, right? This one 20. Okay, and divided with V at going T to infinity. Infinity here, it will maintain the input is 6. So you got it 20 over 6 here. And then K1 minus, this one will be 1 divided with exponent, this one. So of course, you got it 0 here. So the final K, you got it 20 over 6 is 3.333. Okay. So the equation, final one is become here is 3.333. Okay. Alright. Boleh faham tak? When t going to infinity, of course, you will got it, the final value is 20. Okay. And the input one is become 6. That's how you can get it. K value 3.33. Alright. So you want to find the transfer function 3.33 plus 1 plus 0.4s. Okay, ada apa-apa soalan? Is it clear? Okay. Clear? Ada apa soalan? No, doctor, alright? Okay. Do you have any question? No?
No, sir.
Okay, good. Alright, let's take a break for 5 minutes and then we will continue for the next chapter. Is it? Boleh Kita continue chapter yang seterusnya. We will continue at 3. Okay.
Doktor, tanya boleh?
Ya, boleh. Nak bertanya apa?
Yang untuk first degree tadi tu kan?
First degree
kan
ke first order?
First order. Dia kan satu tolak exponent to the power of negative t over t besar kan? Yang tu bukan itu sebabkan Laplace inverse daripada equation tu
Ya, betul.
Tapi bukan ke eksponen negatif T besar T kecil?
T besar T kecil itu
Cuba doktor tengok example tadi tu.
Ya ini Okey, tengok balik. Yang example ni ke?
Kan dia eksponen negatif 0.4 T, dia bukan T over 0.4.
Okay, this one mungkin saya salah tuliskan ni kot. Yep. Jadi sepatutnya equation dia adalah yang ini ni, equation dia. Okay. Equation dia minus T over T. So sekarang ni, kalau yang ini 0.4. Okay, yang ini kan. So yang ini bila you Laplace, so you will got it is betul lah. Kalau yang ini kan, kalau you Laplace, patutnya you akan dapat dia macam ni. 1 over we call it 0.4s plus s here. Okay. So ini dia akan masukkan equation yang first order awak. Okay, so dekat sini dia mesti S plus A. Okay, saya tunjukkan. Mana je? Where is it? Okay. Ini kan? Betul kan? Sepatutnya kalau you nak Laplace, dia kena jadi macam ni kan? 1 plus S, S plus 1 kan? Betul tak? So yang ni,
Betul.
you bawa lah. Dia jadi macam ni. Okay, boleh. So 1 over 0.4 S Y 0.4. Okay. Okay. So, kalau you nampak dia dekat sini, yang TS ni, mana lagi satu ni. Ini second order. Yang contain. Ni. Ni equation dia. Kalau nak dapatkan yang macam ni, dia kena ada TS kat sini. Okay. So, kalau ikutkan equation ni, dia seolah-olah 1 plus 0.4s kan? Betul? Dekat sini you akan dapat minus 1 minus T over 0.4. Okay. Boleh tak?
Okay. Thank you,
So maksudnya yang ini ni ada kesilapan sikit lah. So dia akan jadi apa ni? So ni divided lah kita kata lah. Okay. 0.4. Okay. Tetapi bila you apply infinity, so dia akan jadi minus infinity juga kan? Betul tak?
Yeah.
So you can still lagi dapat 0 lah kat sini.
Okay, Doktor. Thank you.
Okay, thank you for untuk awak ni. Okay, great. Okay, so let's continue our next chapter. Kena cepat juga, tak boleh nak tangguh-tangguh nanti. Okay, nanti tangguh pengajian pula. Alright, so first order settle. So now let's look second order system. Alright, same with the first order system, you will have the what we call it, the general equation for the second order system. Okay, so it will become y over s, right? So I like to write this one lah. Saya suka tulis macam ni. This one k, and this one the general equation for second order omega n squared divided with s squared plus 2 dengan damper omega n s, wow, tak cukup pula, plus omega n squared power of 2 here. Okay, then we got it is ys. Okay, so this is the general equation for the second order, and this is your controller. Okay, so k is what? K, we call it controller, sometimes we call it gain, and theta is what we call it damping ratio, right? Theta, right? Ini kita panggil apa ni? Ataupun panggil epsilon ni. This one, what we call it, theta, right? Apa kita panggil? And then omega n is the natural frequency. Apa? Sorry?
Zeta.
Theta,
Z. Ya.
Okay.
Bukan theta.
So, betul tak? Apa nama? Macam nak cakap, kita cakap je ni. Okay. Alright. Maybe we can ask our doctor and Afdal Alif ni. Okay. Alright. So the example system for the second order is like this one. So you got a spring, and then you got a damper, and then at the center you put it some mass here. And then after that, you come out with a equation here, and then when you apply Laplace, okay, and then you got it this kind of equation. Okay, x naught s and xi s. So this one k and s plus cs plus k, and then k you bring right here. K over m, so m you want to settle out, so c over m s plus k over m. Okay, so from this one we can say that right, so 2 omega n and so on. So it is depending on our damping ratio, our natural frequency here, omega n. Okay, it will depend on k, right, the stiffness of spring and mass, and also our theta here, it will depend on c over m. Okay, so you want to play around with the theta and on the natural frequency, you can play around with this value c and also k, and also it will affect your mass. Okay, and then after I mentioned it before, so this one, the general equation, right, for the second order. And then after that, when you inverse Laplace, you will got it this kind of equation. But we don't use this one in order to plot the graph. There are another way how to plot it. Okay, done. And then the type of response of the system can be identified by comparison of characteristic equation. Okay, the most important thing is you will use this word characteristic equation. So characteristic equation, that's mean s power of 2 omega n s plus omega n squared. Okay, so this one. Alright, and you can put it to 0. So based on this characteristic equation, we can know the behavior of the system. Alright, so for example, this one, the second order system. So by having this characteristic equation, we can know the behavior, the performance, right? If you are given the third order system, so by knowing the characteristic equation, we can know that. Okay, alright. So we can see that the effect of the damper, right? This theta, we call it is the, sometimes we call it damper, right? We have the damper here. So what is the effect? If the theta more than 1, so the graph will be same like a first order system. Alright. If theta equal to 0, what is mean the theta equal to 0? What is mean? Theta equal to 0, that's mean, okay, that's mean you got a spring here, right? And then you got the mass here, right? And then you got it damper here. Okay, mass spring damper. So this damper will determine the value of your theta, right? Theta. Okay. So now theta equal to 0, that means you didn't have any damper here. Okay. So when you pull it, right, you pull the mass, right, this is the K, then you release it, right, so it can make the response become oscillate, right, become oscillate. Okay. So this is what we call it the theta equal to 0. So in between, that means theta less than 1 and more than 0, you will get it this kind of graph, right? There will be some overshoot, and then there will be a stable after that. So you can calculate the statistic error from that. Okay. Okay. So let's look this example. Okay. Now you got it is y s over us, okay, 2 s squared plus 3s plus 2. Okay. Now, wait, someone join all bill. Okay. Right. Okay. So this one is the characteristic equation. First of all, you need to find the characteristic equation here. So s power of 2, 3s equal to 2 equal to 0. Okay, done. This is the characteristic equation. And then you compare with the general equation S2 to delta omega n S plus with omega n squared equal to 0. Okay, done. Alright, so first you find the natural frequency omega n squared equal to 2. Then you just compare, right? Characteristic equation compare with general equation of second order. Then you will got it omega n is square root of 2. Okay. And then number 2, 2 theta omega n equal to 3. Okay. So this one equal to 3 here. And then you can solve it to 2 equal to 3. Then you can calculate the theta here. So you got it 1.06. That means 1.06, the graph will be like this one. We call it overdamp, right? That means it's so many dam here, right? So your mass here, it will stop, right? It will stop, right? Because of the damper here. Okay, so theta more than 1, we call it is overdamp here. Okay, more than 1, so the graph will be overdamp. So the graph will be like the first order. Okay, overdamp. Okay, all right. Then you can solve it by using the partial fraction again. All right, and then for example, your input is step input, right? Step input, you can solve off, and then after that you can use the inverse Laplace again. All right, then you will got it. The final equation is this one, and then how to plot it. So maybe you can put it t equal to 0 first, and then if you got it 0 at y equal to 0, t equal to infinity, and then you got it at 1. Or you can use the MATLAB in order to plot it, right? So I will show you the MATLAB here. So now what is the equation for this one? The easiest one, you just can type it using the Laplace here, okay? 2 divided with s power of 2, yep, 3 times s plus 2, okay? So let's run this one, run session. Yeah, you got it, this kind of graph over time. Okay, yep. Okay, this is graph. Okay, done. Right? Ada persoalan tak? Is second order system is very simple. You just compare it the standard equation, right, for second order, and also you compare it with the characteristic equation here. Do you have any question? No? Is it no? No. Ada persoalan? Tak ada eh? Okay.
No.
Alright. Let's look another example. 4 divided with s power of 2 plus 4. So you just compare it, right? This one, the characteristic equation, compare with the standard equation, standard second order equation here. Okay. So because there is no damper there, so you just compare s squared plus omega n and so on. And then you can get the natural frequency and also the damping ratio equal to 0. So when the damping ratio equal to 0, so the graph will be like this one, right? That means there is no damper, right, for that system. So we call it is undampened, no damper. And then you can solve it by using the partial fraction. This is the example, all right? When you use the partial fraction, this one, right? Because the s squared plus 4, then you need to do like this one. Okay. And then you solve it, and then you apply here. You put it radian and cos and so on. So you will get this kind of graph. Okay, like here. Okay. So in order, you can use the MATLAB, for example. Yep, 4s squared plus 4s. So let's look this one. Yeah, this is the maybe I can put this is right here. One first, this one, the blue color, and then this one, the red color. Okay, so this is the overdamp, right? When the theta more than 1, and this one the underdamp. That means undamp, right? There is no damper, so you will got it this kind of graph, the oscillation. So let's look. We want to achieve at 1, so that means overdamp can achieve it, right? Right, but it will take some time. Okay, and however the undamp, right? Yes, you can achieve the output at 1 more faster than overdamp, but however it's not stable, right? It's not stable. Okay, so that is how we describe our system. Okay, and then next example here. Okay, you just compare it, right? Our objective, we want to find the damping ratio. Okay, the word is damping ratio, sorry. Damping ratio. And then we can find it equal to 0.7071. So that means is more than 0 and less than 1. So we call it is underdamped. So underdamped, that means the graph will be something like this one, right? It will be have a some overshoot here. Okay, and then when you do the what we call it, the partial fraction here, right, bs and so on, you do this one, you solve it. Yep, you can see the solution here. And then after that you will got it this kind of graph. Okay, so how to plot this kind of graph? Okay, there will be some method there. Okay, how to plot it. So let's use the MATLAB how to plot it. Okay, 2 plus 2s here. Yep, this one. Blue, and put it green. Oh no, where is the right? Here, blue, and also, and then after that, red. Yep, after that, green. Yep. Okay. First, the blue color one is overdamped, and the red color one is undamped. There is no damp, and the green color one is what we call it, underdamped, right? Okay, undamped, underdamped, or damped. Okay. Damn. Alright. So you can see that the green color one, right? When the underdamp, right? So that's mean the time response will be more faster than overdamp here, right? But it will have some overshoot here, right? But at the end, if we got it, the statistic error is equal to 1, right? The error equal to 1, okay? So how to plot this graph, right? The green color one, how to plot it, right? There will be a method, right? There will be some method and some procedure that we can follow, right? How to plot this kind of graph we can follow, right? So we will do this one and so on. So we will do this one on next week. Okay, right? So that's it for our class for today. I will see you again on next week. Bye bye. Assalamualaikum and good evening to all of you. Okay.
Waalaikumsalam. Thank you, Dokter.
Waalaikumsalam.
Waalaikumsalam. Okay.